Every time you flip a switch, electricity appears instantly. Lights turn on, devices start working. Most people never think about where that power comes from, but electricity doesn't start inside your walls. It travels long distances through a massive system built to run every second of every day. When that system works, life feels effortless. When it fails, everything stops. To understand modern life, you first need to understand how electricity actually reaches your home.
Electricity begins at power generation facilities that are designed to operate continuously, day and night. These facilities convert different forms of energy into electrical power. Fossil fuel plants burn coal or natural gas to heat water and create steam that spins large turbines. Nuclear power plants use controlled nuclear reactions to produce heat for the same purpose. Hydroelectric plants rely on flowing water to turn turbines directly, while wind turbines use moving air. Solar power plants convert sunlight into electricity using photovoltaic panels. No matter the source, generators must spin at very precise speeds to maintain a stable electrical frequency. Power plants cannot instantly start or stop without consequences. Output must be adjusted carefully to match real-time demand across the grid. If generation does not match consumption, instability occurs. Every light, screen, and appliance in your home depends on power plants operating correctly and continuously.
Electricity generated at power plants starts at relatively low voltage, which is not efficient for long-distance travel. Sending electricity far at low voltage would cause significant energy loss as heat. To prevent this, electricity passes through step-up transformers located near power plants. These transformers increase voltage to extremely high levels, often hundreds of thousands of volts. High voltage allows electricity to travel long distances with minimal loss. Step-up substations contain massive transformers, cooling systems, and protective equipment that operate continuously. These facilities are critical transition points in the grid. If a major transformer fails, large regions can lose power instantly. This voltage increase is essential for connecting distant power plants to cities and towns. Without step-up substations, modern electrical grids would not be possible, and electricity could never reach homes efficiently from faraway generation sites.
Once voltage is increased, electricity enters the long-distance transmission network. High-voltage transmission lines carry electricity across vast distances from power plants to cities and industrial areas. These lines are supported by tall steel towers and spaced far apart to prevent electrical discharge. Transmission networks are designed with redundancy so electricity can reroute if one line fails. Grid control centers monitor power flow constantly and adjust routes to avoid overloads. Weather events such as storms, heat waves, and ice can damage transmission lines and reduce capacity. When multiple lines fail at the same time, large-scale outages can occur. Transmission systems connect remote energy sources to dense population centers. Without this stage, electricity generated in rural or remote areas could never power modern cities or homes.
Electricity cannot be delivered directly to cities at extremely high transmission voltage. Step-down substations reduce voltage to safer levels, suitable for regional distribution. These substations act as gateways between transmission lines and local networks. Large transformers lower voltage, while switchgear directs electricity along different routes. Protective systems detect faults and automatically isolate damaged sections to prevent wider outages. Substations must respond instantly to changes in demand and equipment conditions. Many are located near cities, but remain unnoticed behind fences and security systems. If a major step-down substation fails, entire neighborhoods or cities can lose power. This stage transforms dangerous high-voltage electricity into a form that can safely move closer to homes and businesses. From step-down substations, electricity flows into local distribution networks.
These networks consist of overhead power lines on utility poles and underground cables beneath streets. Distribution systems deliver electricity directly to neighborhoods, schools, offices, and shops. Voltage levels are lower than transmission lines, but still higher than what homes can safely use. Distribution networks must handle constant changes in demand caused by weather, daily routines, and seasonal patterns. Hot afternoons, cold nights, and holidays all increase load. Failures at this level usually result in local outages rather than regional blackouts. Because problems are isolated, crews can restore service relatively quickly. This stage is where electricity becomes part of everyday life, moving through streets and neighborhoods toward individual buildings.
Electricity reaching neighborhoods is still too strong to be used safely inside homes. Before entering houses, power passes through neighborhood transformers. These transformers are the cylindrical units mounted on utility poles, or the green metal boxes placed on the ground. Their job is to reduce distribution voltage to safe household levels. Each transformer usually serves a small group of homes or buildings. As people turn appliances on and off throughout the day, electrical load constantly changes. Transformers must handle these fluctuations without overheating. If a transformer is overloaded or damaged, it can fail and cause a local outage affecting only nearby homes. Crews can replace or repair these units relatively quickly compared to larger grid components. This final voltage reduction step is critical. Without neighborhood transformers, electricity would be far too dangerous to use inside walls, outlets, and household appliances. After voltage is reduced by neighborhood transformers, electricity enters your home through service lines. These lines connect to an electric meter mounted outside the building. The meter measures exactly how much electricity is used, which determines billing. From the meter, electricity flows into the main breaker panel inside the home. Circuit breakers divide electricity into separate circuits for lights, outlets, and major appliances. If too much current flows through a circuit, the breaker automatically shuts off power to prevent overheating and fires. Inside walls, insulated copper wires carry electricity safely to every room. Electrical codes exist to ensure wiring, grounding, and protection systems reduce risk. This stage is where electricity becomes personal and directly usable. Every light switch, charging cable, and appliance depends on this carefully controlled delivery into the home. Electricity systems must balance supply and demand every second of the day. Unlike other resources, electricity cannot be easily stored at large scale. Grid operators monitor usage in real time using sensors and control systems. When demand increases, such as during hot afternoons or cold evenings, power plants increase output. When demand falls, generation is reduced. Automatic systems help maintain stable frequency and voltage across the grid. If balance is lost, protective systems can shut down parts of the network to prevent damage. Large imbalances can trigger cascading failures. This balancing process never stops, even late at night. Electricity feels constant and reliable only because thousands of adjustments are happening continuously behind the scenes to keep supply and demand perfectly aligned. Blackouts occur when parts of the electrical system fail or are intentionally shut down to prevent damage. Common causes include severe weather, equipment failure, accidents, and sudden spikes in demand. Storms can knock down power lines, while heat waves can overload equipment. Protective systems are designed to disconnect sections of the grid when faults are detected. This prevents failures from spreading further. Some outages affect only a few streets, while others impact entire cities or regions. Restoring power requires careful inspection, repair, and step-by-step rebalancing of the grid. Crews work around the clock to restore service safely. Blackouts reveal how dependent daily life is on electricity, as communication, water supply, transportation, and healthcare are quickly affected when power is lost. Electricity feels invisible because the entire system is designed to work without drawing attention. Power plants are located far from cities. Substations are fenced and quiet. Control rooms operate remotely. When electricity flows smoothly, it feels automatic. In reality, engineers, technicians, and operators constantly monitor the grid. Maintenance crews inspect lines, transformers, and substations every day. Software systems detect abnormalities before people notice problems. Electricity does not simply exist on its own. It is actively managed every second to keep homes, businesses, and cities running. The reason most people never think about electricity is because the system succeeds at hiding its complexity. Only during outages does the massive effort behind reliable power become visible. Electricity doesn't appear by magic. It travels through a vast system built to work every second. From power plants to your walls, thousands of components must work together perfectly. Once you see the system, you start noticing how fragile modern life really is.